this video, we're going to use the first principle to find the derivative of sine of x, and I'm going to make it really simple for you to understand it in case you've been struggling. So we're going to find d over dx of sine of x. And if you remember from your class, with the first principle, we're using a formal limit definition for finding a derivative, right? So what we want to find now is the limit as h approaches 0 of sine of x plus h minus sine of x all over h. And the idea, right, is that as h is getting super small, we are essentially finding what the derivative of sine of x is. And if you remember your identities, what does sine of x plus h tell us? We can actually use a really cool identity here where I can rewrite sine of x plus h as sine of x cosine of h plus cosine of x sine of h all minus sine of x. And we're going to make sure to not forget this limit notation right here. This whole expression gets divided by h. And so maybe many of you got stuck here because it looks nasty, right? And it might not be obvious of how to simplify this, but what if I told you that I can move this sine of x term here closer to the sine of x on the left? Because as you'll see, that's going to let us factor things out quite a bit. And by rewriting this limit now, we're going to have sine of x cosine of h minus sine of x plus cosine of x sine of h all over h. And so what I'm going to do now is I'm going to go ahead and factor out this sine of x term here. And so now we're going to have the limit as h approaches 0 of sine of x all times cosine of h minus 1 and this is going to be added to cosine of x times sine of h. You might be wondering, Dave, what was the point of that? Is that really helping us out? Well, here's the cool thing. So we want to know, okay, this part here, can I break this up into two separate limits? And can I do this? You tell me in the comments below if you think this is actually allowed. So now I'm going to multiply the limit as h approaches 0 of sine of x times this expression's limit now. So the idea, right, is that you can only split up limits like this if for each part you can show that, hey, the limit actually converges to a number. And we're going to do just that because this limit right here as h approaches 0 of sine of x is pretty trivial. Do you notice that sine of x does not have an h in there? So it's essentially keeping the x fixed almost as if it's a constant. So the limit as h approaches 0 of sine of x is just going to give you sine of x itself. But then we need to show whether or not this limit as h approaches 0 of cosine of h minus 1 all over h converges. Many of you might actually know the answer. Tell me below if you know it. So to give it away, the answer is actually 0 for this. If you know why, or if you already learned this, feel free to skip ahead. But for those who are ninjas that really want to understand this math, I'm going to show you here just in a bit how you can prove that. Let's first not forget this other term here. And now I'm going to go ahead and focus on this expression to show that the limit as h approaches 0 of cosine of h minus 1 all over h actually equals 0. I talk about this in other videos, but you can use this idea of multiplying the top and the bottom by what's called the conjugate of the top. So the conjugate of cosine of h minus 1 looks very similar, but you flip the sign. So instead of cosine of h minus 1, I'm going to multiply everything by cosine of h plus 1 on the top and bottom. So for right now, I'm just focusing on only finding this particular limit. We'll move to everything else in a bit. This becomes cosine of h plus 1, and then all over h times cosine of h plus 1. Looks pretty gnarly, right? I mean, this is pretty complicated looking, but it's okay. Because what I'm going to first do is simplify the top by just multiplying everything through. Now, does the top look familiar to you? Do you remember that we have these identities? One of which is this very famous one, sine squared of h plus cosine squared of h equals 1. So if you were to solve this expression for cosine squared of h, you would get 1 minus sine squared of h, right? So then this limit will become 1 minus sine squared of h minus 1. So the 1 and negative 1 will cancel out, right? Leaving you with just negative sine squared of h on top. So this is where we get to use a really cool trick, and maybe it hasn't been obvious to you guys. But you can be very clever now in factoring out this fraction and breaking up the limit strategically. What I'm going to do is, in my head, I already see, I need to fix this right here, that I have sine of h and an h on the bottom. So I already should know that the limit as h approaches 0 of sine of h over h comes from the squeeze limit theorem, right? We know that that converges to a 1. So thinking ahead a bit, I'm actually going to go ahead and pull out that sine of h from the top out. And the h on the denominator is going to be pulled out with it. So you're going to have this right here, multiplied by the remaining stuff that we didn't pull out, right? So you still have a negative sine of h on top, all over cosine of h plus 1. And again, you might be asking, well, are you allowed to do that? Well, the answer is yes, because we can show that these two limits actually converge. Sine of h over h on the left here comes from the squeeze limit theorem. That's going to become a 1. And then for the right-hand side, you can now actually plug in 0 directly, because on the denominator, cosine of 0 is a 1. So 1 plus 1 will give you a 2. But then on the top, negative sine of 0 is just 0. So now we have a product of a 1 and a 0, and that shows that this whole thing equals a 0. So what I'm going to go ahead and do now is go back up here. We know now that we just demonstrated this right here all is a 0. So 0, and then on its left, you have sine of x, right? That's fixed. Sine of x times something that's converging to a 0 means that this whole entire thing here is going to go to a 0. Leaving us with just this right here to prove that it's going to simplify to cosine of x, because we're trying to show that the derivative of sine of x is going to give you cosine of x. So I'm going to go ahead and write that down. And before we get into that one, by the way, if you're really finding value in this, guys, feel free to smash that subscribe button. And if you want a little break from your studying, I know it gets kind of hard. If you want to keep your mind fresh, check out Number Ninjas. It's a game I made for free for you in the description below. So now I'm just going to write that limit down here. Cosine of x sine of h all over h. So we have the limit as h approaches 0 of cosine of x sine of h all over h. And now we need to show, hey, this simplifies to cosine of x. Well, we can be strategic once again in pulling out our limit here, because I see now that I have sine of h over h in this expression, right? So why don't I just do this? Rewrite it as the limit as h approaches 0 of sine of h all over h times the limit as h approaches 0 of the remaining part, which is just cosine of x. We know that this right here is going to be a 1, right? This expression on the left-hand side from squeeze limit theorem. And then this right here, check it out. Cosine of x does not have an h in there. The h value converging to 0 is doing nothing to this. This is remaining the same. And so our final answer is just simply going to be cosine of x. Pretty easy, right? Wasn't too bad. Hope you enjoyed this video, and if you want some more derivative practices, check out the next video you see on your screen.